All right, welcome everyone. So in this video, I want to just do a quick little refresher on how we diagonalize symmetric matrices. And that process is a little bit special when our matrix A is symmetric, and then see how we can apply this process to quadratic forms and maybe find a nice set of variables to express the quadratic form. But before we get there, let's just review this process on how we diagonalize a symmetric matrix. So let's consider the matrix A, which has diagonal entries 1 and -5. So it's a 2 by 2 matrix, and the off-diagonal entries are both -4. So this is symmetric. So that means it's orthogonally diagonalizable. So that means we can express A as a product of P times D times P transpose, where P is an orthogonal matrix. So what it means to be an orthogonal matrix is that the columns of this matrix P are orthonormal. Okay, and so we're going to set up matrix P by choosing a set of orthonormal eigenvectors from column A. And so if A is not symmetric, we still may be able to diagonalize matrix A. Just in the general case, that looks like A is equal to P times D times P inverse. And here we have this nice special case. When A is symmetric, it turns out that we can set up this matrix P so that it's orthogonal, and therefore the inverse of P, which usually might be very difficult to compute, is simply just the transpose of P. Okay, and so since this matrix P that we're going to first find is constructed from eigenvectors of matrix A, the first thing that we're going to want to do is find the eigenvalues for matrix A. And so a quick refresher on eigenvalues is we would set up the characteristic equation, try and factor the quadratic equation, and find the roots of the quadratic equation. In this case, the roots are -7 and 3. So that's where these two eigenvalues come from. Then we want to go ahead and find the eigenvectors. And just a quick recap of that process, for the eigenvalue 3, we subtract 3 from the diagonal entries, and this gives us the matrix that has a top row -2, -4, and a second row of -4, -8. So we get redundant set of equations that we need to solve to find possible eigenvectors for lambda 1 is equal to 3. So in this case, taking the top row, we get the equation that -2x1 is equal to 4x2. So in other words, x1 is equal to -2x2. And then setting, for example, x2 equals -1 would give us x1 is equal to 2. And similarly, with the eigenvalue, lambda 2 is equal to -7, we can find an eigenvector, which is 1, 2. So now we've got two linearly independent eigenvectors for the matrix A. So we can diagonalize it, and moreover, we can diagonalize it in such a way that this matrix P that we choose is an orthogonal matrix. So next, we would want to take these two vectors that we found, and if possible, find an orthonormal set of vectors that spans the same space. And so in this case, we don't need to do anything. That might involve using the Gram-Schmidt process to generate a set of orthogonal vectors. But because our two eigenvalues are distinct here, we can see that the corresponding eigenvectors are orthogonal to each other already. So we don't need to worry about Gram-Schmidt in this case, because we have two distinct eigenvalues and their eigenvectors are going to be orthogonal. If you had like a double eigenvalue with multiplicity 2, then it's possible that the eigenvectors you find for that eigenspace are initially not orthogonal to each other. And so you may need to use Gram-Schmidt along the way, but here that's not an issue. But now we do want to normalize these vectors. So for example, V1, it has a length of square root of 5. And V2, that also has a length of square root of 5. So we're going to scale both of these vectors by their corresponding magnitudes, which in general, they may have very different magnitudes. So the factor that we scale them by may be different. But in this case, both of these vectors have magnitude square root of 5. So we can just scale them by 1 over the square root of 5. So down below, we've got first our matrix P, which consists of the first column is vector v1 that we've normalized. And then the second column is vector v2 after we've normalized it. Next comes the diagonal matrix D, where now these entries, the ordering is going to be consistent with how we list the eigenvectors across the column. So the first column was an eigenvector for the eigenvalue 3. So 3 is the first diagonal entry. Then goes the second eigenvalue of -7. And then here's where we get to save ourselves some trouble that normally I would need to find the inverse of P, but because this vector is orthogonal, we know that the inverse of P is the transpose. So over here, rather than take the inverse, which involves possibly many operations if you have large matrices here, the transpose operation, that's much more basic. And so here's this really nice property that when we diagonalize symmetric matrices, we can do so with our matrix P chosen so that it's an orthogonal matrix. And now let's see why this diagonalization of symmetric matrices is particularly nice when we apply it to quadratic forms.